Okay, hi guys, Mr. Rocco again. This is the third and final video for this week, the week of, what is tomorrow? The 19th, October 19th. Again, everything's due by Friday, this Friday the 23rd at 3 p.m. 3 p.m. So let me get into this video. This one is talking about a field. So we covered rate of change in the first topic. Rate of change was change in a field or field value divided by time, right? If you're looking at, there was a lab that had the balloons and it said how many meters per minute was the balloon increasing in the air. So that's a field. In this case, you're looking at altitude, right? How high the balloon is going, meters. So a field is any region of space or environment that you can measure. And these are some examples of fields, things you would measure in science. So temperature, right, how many degrees it is outside. Humidity, right, what percentage of the air is full of water vapor. Elevation, right, what's the height above sea level. Air pressure, how many millibars of pressure it is outside, whether it's a cold high pressure day or a warm low pressure day. And depth, maybe the depth of a lake or the depth in meters of an ocean. So those are examples of fields. Something that you can measure is a field. Then there are two types of fields. And this gets a little bit more. This will be coming up probably when you take physics, but cover it in earth science, just the basics. So there's what they call a scalar field. SCALAR is a scalar field. A scalar field, you measure, but you get a number only. What they call a magnitude. Usually you hear the word magnitude when you're talking about earthquakes, right? What was the magnitude of the earthquake in Southern California? It was a 5 on the Richter scale or a 6 on the Richter scale. In earth science, there are some scalar fields, ones where you just use an instrument and you get a number. For example, temperature, right? You use a thermometer and it'll tell you it's 25 degrees Celsius outside. So that's a scalar field. There's no anything to it. Just read the number and that's a scalar field. Or pressure. I look at a barometer and it tells me that it's 995 millibars of pressure outside on the barometer. Or humidity, right? I calculate the humidity. Now, this is an instrument. We'll use it when we get into weather. It's called a sling psychrometer. It's actually got 2 thermometers on it, and I'll show you the steps how to use it. But it'll calculate the humidity outside. What percentage of the air is humid? Maybe it's a very sticky day, so it's 80% humidity. So those are examples of scalar fields. The other type of field, and again, this is covered a lot in the course when you take physics, is what's called a vector. A vector has to have 2 things. So a scalar just has a number. A vector has a number, but it also has a direction. And the best example of a scalar field in earth science is the wind. When you talk about the wind, let's say it's a breezy day, it's kind of chilly outside in Rhinebeck, the meteorologist on television will tell you 2 things. How fast the wind's blowing, maybe it's 15 miles an hour, and they'll also tell you the direction the wind is coming from, which a northwest wind is usually a cold wind. Anything north-northwest. So they're giving you a vector. 1, the wind direction, or well, wind speed, I should say, 15, and then the direction the wind is coming from, the northwest. So when you have a number and a direction, those are vectors. I gave some other ones up here besides wind. Weight, right? Weight is affected by the force of gravity, which goes back to last week talking about, not Polaris, but gravity and the earth. Everything is pulling toward the center. Gravity wants to pull everything to the center of our planet, right? If you drop something on the floor, it's heading toward the center of the earth. Obviously not going to make it because it hit the floor and the floor stopped it, but that's where it would go. So if you could wipe away all the surface and wipe away everything and just have the you in the center of the earth, it would take whatever you drop and pull it right to the middle of the center of the planet. So that's a direction, right? Going down into the middle. That's weight. Acceleration, you're looking at what direction, right? You're on Route 9 at a red light and then you hit the gas. You're accelerating, right? So many miles per second. You're heading in a certain direction as you accelerate toward Red Hook, let's say. And again, gravity is also a vector because it tells you how much and what direction it's heading. So wind is probably the easiest to remember. So wind what direction is the wind coming from, and how fast. And that's why they're called vectors. Then we switch gears and we talk about isolines. So in math class, and again, it's been a while since Mr. Rocco's taken a math class, but again, I was pretty good in math. There's what's called an isosceles triangle, right? An isosceles triangle has equal sides. So isosceles, the prefix iso, take just iso, it actually means same. And then a line is a line, right? Connecting points. So an isoline is a line that connects same value. Same value. So if you remember what an isosceles triangle is in math class, where you have equal sides, you have now equal values. There's some very important rules about isolines, and this is pretty crucial here because we're going to be spending a lot of time with isolines these next few weeks. Isolines can never cross or touch, right? If this line represents 100 degrees and this line represents 110 degrees, put numbers on them so you know what they are. So the values, this is 100 and this is 110. You can't take this 100 line and cross the 100. Because what are you telling me? Then if at this point where the 110 crosses the 100, you're telling me that 110 is equal to 100. And that's not the case, right? 110 is not 100. So they can never touch. They can get very, very close. You could have, let's say this line represents 10 degrees. And this line represents, I'm going to draw 12. We're counting by twos. You could have the 12 degree line come very, very close. Right, something like that. And you have to excuse me, mouse is not easy to do with, but they're never going to touch and they're never going to cross one another. If there's a box, and you'll see this, I have an example here in a minute. If they give you a box, and this is typical, they'll give you some values in here, they'll put some numbers, and the directions tell you to, they might say that your isolines, when you draw them, they should touch the edge of the map or touch the edge of the box. If they say that, then yes, you have to make sure they touch the edge of the box. And I'll show you a couple example where they do and an example when they don't. Now, isoline is sort of the broad term. Underneath that, you have three specific examples of isolines, and we're going to draw a couple of these in this video. So isotherms, a therm is heat, right? Therm, like a thermos, right? Keeps your hot cocoa warm. So anything therm or thermometer has to do with temperature. So isotherm, meaning same temperature. Lines that connect equal temperature. Isotherms. Isobars, right? The instrument that measures air pressure, which a lot of you know, is called a barometer. So iso, meaning same, and bar are ways you measure pressure. So they're called isobars. And we'll draw an example of that here too. And then this one doesn't follow the iso pattern. So you got isotherm, equal temp, isobars, equal pressure, and then they're called contour lines, which we're going to be spending a lot of time on these next few weeks. Contour lines connect equal elevation. Again, if you're looking at a hill, and I'll show you an example of that, where the lines represent different elevations, a bird's eye view. Contour lines are showing you bird's eye view, looking down on a hill or a mountain, using lines to show elevation, equal elevation. And I'll show you an example of that too. All right, this map is actually they call it an isothermal map. It's using isolines to connect every 5 degrees. So you can see up here, you've got New York City, for example. There's a 65 degree isotherm, but that isotherm not only stays in New York, if you follow that 65, goes through Michigan, Wisconsin, Minnesota, to the Dakotas, takes a dip down here toward Colorado, back up again. You know, it goes the whole way across the country. What does that mean? Anywhere along that red line I just drew, 65, is 65 degrees. Those are all towns and cities sitting at 65. If I go to the next line down, that's the 70. So I start in New Jersey, Pennsylvania, Ohio, close to Michigan, Indiana, Illinois, Wisconsin again. But anywhere along this purple line is exactly 70 degrees. I connected a bunch of cities and towns with 70 degree readings. If I go down here to Virginia and North Carolina area, that's 75. So that's the 75 degree isotherm. So these are called isotherms. You're connecting equal temperature. Whoops. Again, notice they don't cross, they don't touch. I shouldn't have touched there. But you see the lines don't cross. They can zigzag, and you can see they kind of snake around, pretty wavy looking, but they never cross and never touch one another. Here's the 80. Goes through North Carolina, South Carolina, Georgia, Alabama, Tennessee, Missouri, going across the country. That's everywhere along there is 80. When I get down here toward Mississippi and Alabama, I've got the 85 degree isotherm. Right, I get into Texas, I've got the 90 degree isotherm. Why do you need isotherm maps? They help you pinpoint where the air masses are cold and where the warm air masses are. So let me clear this right away. And the Weather Channel does a good job with isotherm maps. They use these colors, so you can clearly see right away using colors. That's why pie graphs are great when they use color to show data quickly and easily. I can see just looking at this map without much effort where's the warmest air mass. Well, gee, way down here in Arizona, looks like I got some 9500s. Where's the cooler air? Oh, I got some cooler air up here in Maine. I've got some cool air up here near Seattle. Right, I've got some very cold air way up here by Hudson Bay up in Canada. So I can quickly see, using these isotherms, where's the cooler air masses, where's the warmer air masses. They're good. Meteorologists use these for forecasts. So they could sit there and say, well, I see this cold air mass sitting up here in Canada. Where's it going next? Is it going to head straight to the east and stay ahead above the United States and not affect us? Or is this a cold air mass going to start sliding this way toward New England and New York? And therefore they will then make an inference. They'll make a forecast and say, well, we think in the next 3-4 days this cooler air, these 40s and 50s, are going to slowly work their way down, and New York, that was now sitting Rhinebeck in the 60s, is now going to drop into the 40s, right? So they use these isotherm maps to make good weather forecasts. Okay. Here's an example of how you draw isotherms, and probably the best way to do this is, and I think I gave you maybe a few of these to do on a homework. Going to be tough to do on a computer with the mouse, and you'll see I have a tricky time trying to draw lines with a mouse. You might want to, if you have a printer at home, and I hope you do, most of you do, print out maybe some of my assignments this week. At least I know that the third assignment that has the isotherms. So any of those ones that have anything we have to draw on, you might want to print it. Maybe take a pic of it after you're done with your phone, and then upload that when you submit your assignment to Canvas, just because it's going to be easier for you than trying to draw with the mouse. But I'm going to attempt it here. So let's say I'm drawing isotherms, and this one, they want you to draw them every 1 degree. And it would say in the directions, I didn't write it here, but it would say, make sure your lines touch the edge of the map, which means they have to start and finish on this box. So isotherms are equal temperature. The next thing I do, I look at all my numbers. I try to figure out what is the highest and lowest number. So I can see I've got a 25 degree number up here. I've got a 30 degree number down here. So my lines are going to go from lowest to highest as I work my way from top left to bottom right. Again, rules, you don't want your lines to cross, and you want to connect your equal numbers. The dots, when they give you dots next to it, that's what you want to go through. So it's connecting the dots. The number is just telling you what that dot represents, but your line should go through these points. So right now I got 125. I'm going to start up here on the box right here. I'm going to come down. I'm going to hit this 25 point, and then I'm just going to end it on this side of the box over here. Again, I started on the box and I ended on the box. And it'll say it in the direction. Make sure your line extends to the edge of the box or edge of the map. I got 26s. I've got one here, one here, one here. I'm going to connect them. So I'm going to start up here. I'm going to go 1, 2, 3, and touch the edge of the box. When you draw, anytime you draw these isotherms on maps and stuff, always use a pencil. That's the best tool, because if you make a mistake, you can erase pencil, especially on a test or the regions. You want to always use pencil. They will tell you that on the directions, and I will remind you that when you take the regions. You use pencil for maps, graphs, drawings, diagrams, anything like that. Anything that's a written answer where you got to explain something in a sentence, that would be done with a pen. But anything like this, especially isotherms, isolines, you always use a pencil. So you don't have to worry about making a mistake and then it looks messy. All right, 27s. I got 1, 2, 3, 4. Same thing. I start on the edge of the box. I hit this 27 here, 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 and to the edge. And I just keep the pattern going. And this is a very easy one. I didn't want to start you out with a tricky one. I gave you a pretty simple isotherm map. Start here, 28. Oops. And I missed it. 1, 2, 3, 4. Now, where could you go? Left or down? Either way, doesn't matter. I could end it down here. I could have gone over this way, as long as I touch the edge. Don't go past, like somebody I know, I've had kids in past years say, well, if I did this 25, what if my line went like, whoa? Yeah, they're going to mark you wrong for that. And you also don't want to come up short either. Like, I'm trying to think if a student does, oops, my eraser tool. So if a kid does something like that, the kid maybe touches on this edge, but does not actually touch the box over here. Yeah, they're going to mark you wrong there too. So just make sure it's, just right, touching the box. 29. I could start up here on the top of the box. I could start on the right-hand side. Doesn't matter as long as I'm touching the box. 29. 1, 2, 3, like that. And then 30 here. Here, down. And that's my isotherm map. I drew them every 1 degree. I believe I gave you, like I said, a couple of these to do for homework. One, you have to do them every 1 degree. I think one of them I gave you every 2 degrees. So if it says a 2-degree interval, then what are you going to do? You might only do the evens. So you would not be drawing the 25 and the 27 and the 29. You would only draw, all right, then this is going to be messy, but just to show you, you might draw the 26, the 28, right, and the 30. So these would be left out. You would not be drawing this one, and you would not be drawing this one. Oops. And you would not be drawing this one. You're only drawing the even numbers. So you have to read the directions carefully. It'll tell you you're doing every 1 degree, 2 degrees. And again, pencil, 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 pencil. That's the best thing to use on these. This is a different one. So in this case, I wrote up here, we're going to draw, and these are not degrees. That was temperatures. These are elevations in feet. So we have a piece of land. We're looking down on it, and we're going to be drawing contour lines, which connect equal elevation. So we're going to draw the 25-foot, the 35-foot, the 45-foot, etc. But notice it says do not touch the box. These are going to be more like circles. And let me show you an example of what this would look like. So here you see in this I'm going to spend a lot of time on these. These are called topographic maps. I take the first 3 letters, it tells you what you're looking at. It's a top view. So this map right here is the topographic map. You're looking down on the earth using these contour lines, these iso lines connecting feet to show hills. When you have these kind of circle in a circle in a circle in a circle like a bullseye, that's supposed to represent a hill. And you can see over here you have Able Hill. And then over here you have another hill, actually. You have Baker Hill, which is also circle in a circle in a circle in a circle. And you notice they're drawing contour lines every 10 feet. So they drew the 10-foot, 20-foot, 30-foot. As you go higher up and up the hill, notice the circles get smaller inside each other and the elevation numbers go up. So the 10 is this elevation out here on the hill, right? 20 feet, 30 feet, 40 feet, 50 feet. So you're working your way in. But again, this is a top view. Obviously, this is a side view showing you what it should look like when it's done. So if I go back to this, I'm going to notice look at my numbers. I see I got 65 feet in the middle. That's the peak of the hill. Notice around the outer edge, I've got my 25s. So that's going to be my first circle. I want to make a 25, but go all the way around in a circle like this around the outside. And then I'm going to keep making these smaller circles as I work my way to the middle. Again, making sure, rules, you don't cross or touch each line. They should never touch each other because they represent different elevations, right? 25 is not 35 and 35 is not 45, etc. So let's start with the 25. And again, it's much easier to do this actually in my room. Wow, that was bad. It's much easier to do this in my room on a board than it is with a mouse on a table, but I'm going to do my best, so bear with me. Come around here, I'm going to have to take like sections. 25. Maybe it's because I'm getting old. I don't know. Okay, there's my 25. maybe you guys hopefully are better at mouse drawing than I am. Here's my 35. It's not that easy, but Mr. Rocco can do it. 35. Right? Notice. Now I keep going. 45. And again, when you have these contour lines, one inside the next, that represents a hill. In this case, it's a hill. Now, the numbers could be higher. You could have 2,500 feet, 3,500 feet, 4,500 feet. It would be obviously a mountain, not a hill. All right, so 45, 55. And 65. So here, you don't want to make a line across. That's not really a circle or an oval. You want to go like this. 65. Okay. So that's going to show you this sort of, they call them concentric circles, actually. Bullseye, or the symbol for the target, right? Target stores, they use the bullseye. So when you have these circle and a circle and a circle, that's a hill. And notice in this case, I did not go to the edge of the map like the last example. This one I started and ended, right? And the directions would have said that here. I didn't write it there, but it would have. This one would have said you don't have to, or in this case, you would know. When you're doing contour lines, typically, when it's a hill, you're not going to connect to the edge of the box. You would just go around in a circle. Let's see, that we did. All right, so here's another one. This is actually off of Regents. So on this one, they gave them isobars, which again is an isoline, equal pressure, right? Barometer measures pressure. They only want them to draw, and that's the other thing. Read the directions carefully. The 1,000 and the 996. So you're only drawing two isobars, the 996 and the 1,000. Now you can see they've drawn a few already for you. And notice the numbers are getting lower as you go to the low. See the low pressure? Low pressure, and we'll get into that in weather, is a storm. So when you work your way from up here toward the low, the numbers are dropping. So this is the 1016, 1012, 1008, 1004, which is typical. You notice the increments are every 4 millibars, right? So we're now drawing the 1000 and the 996. So what I would do, and again, you'd want to use pencil, find any numbers that are exactly 1000, take your pencil, put a little line under them, like I see this is 1,000, 1,000, 1,000. Let's see, 1,000. I'm looking for all my thousands. I think that's it. Then you want to think sequentially, right? Where is 1,000? It's greater than 1,000. You do the greater less than 1,000 or 999, but less than 1,001. So I want to try to use that counting in sequence to figure out which way I go with my 1,000 line. All right, and that's where, and also looking at, okay, as I go toward the low, the numbers are getting lower. So when I draw this 1,000, let me draw under them again. 1, 2, 3, 4. I think it was just 4. I'm going to start with this 1,000. This is 998. I want to keep that on the inside. And this is 1,004 over here line. So I'm going to go from this 1,000, and you want to go slow, hit this 1,000. Now you see here I got 997, 1002. Well, where do I go? In between them. And I go to this 1,000 in Florida. And you want to go like one step at a time. Then I'm going to go over here. Now, I got to be careful because some kids, I'll just go this way. But remember, you got a 998 down here in the Gulf. So actually, where would 1,000 be? In between, right? Greater than, less than. Keep thinking greater, less than. It's greater than 998. I got to go between them. So I got to come down here, then turn, then go up, hit this 1,000. Now I look up here. You're kind of like looking ahead on the road. Which way am I going? 999, 1002, right? Go in between them. I go up here, 997, 1001. Go in between them. There's a 999, 1001. Go in between them. And I'm going to come back around to my 1000. Now, that's why I said it's very important to use a pencil. If you messed up, you can erase it. See, and this is on a Regents now. If this was a Regents exam and it happens, a student might use a pen, then they raise their hand. Mr. Rocco, I messed up. What do I do? Can I get another booklet? No. What? So you got to be careful. Use a pencil so you can go back and erase. If let's say your line, you went out here by mistake, you can go back and erase it easily. Excuse me. So there's my 1,000. Then I'm doing 996. So I'm going to, again, underline my 996s. I got one here. I got one here, and I think that's it. Oh, I should mention, you can underline these with a pencil on the regions, but then what you really need to do is go back and erase those lines. I think usually a student will say, can I leave those little tiny lines there that I underlined? No. So go back and erase them so that they're not stray marks, because you don't want to make stray marks. And then maybe just touch this in a little bit. Yeah, don't leave those underlines. I like to tell kids to leave the line there for now just till you see them, so it kind of shows you where they are. But yeah, you got to go back and erase those stray marks. Don't leave them. So I got a 996, I got a 996, and I think that's it. So I'm going to start with this one, right? This is 993, so this is pretty simple. I'm going to come around, hit this one. I'm coming up here. This is 997, 993, so I'm going in between them. This is 995, 999. I go around the 995. And then I come back over to my 996. And then again, I take my eraser, get rid of those little stray marks, fix my line because I'm using pencil, and I have my 2 isobars. And I think I gave the answer key here. Yep. So you see, if you look at where mine is here and go back, looks the same. And this one here was the 1000, and there's the 1000 line there. So that's how you would do those isobars. And you'll see some of these as we move forward here the next couple weeks. All right, the last thing is gradient. So gradient is also slope, which you do in math class. You might call it rise over run, or what is it, change in y over change in x. You're looking at a vertical change versus a horizontal change, going vertically versus horizontally. The formula for gradient of the equation is right on your reference table. So we've looked at rate of change and density so far this year. Here's the equation. It's right on page 1. If you go to your reference table, change in a value, something measured, divided by distance. It's very similar to the equation for rate of change. Actually, the only difference between this formula and rate of change, this is distance on the bottom, and the rate of change, you get rid of this and you make that time. So that's really the only difference. They're both change in a field. One's time, one's distance. So here's a simple example. Let's say you have a weather map. You have 2 cities. The 2 cities are 240 miles apart, and there's a difference of 12 degrees between them. When they will say calculate the gradient. In this case, my units, because distance goes on the bottom, is going to be degrees Celsius per mile. How many degrees Celsius per mile is the gradient between these 2 cities? So then they might give you a weather map to show you the 2 cities. So I've got a city over here in Nebraska sitting in this cold air at 28 degrees. I've got a city over here in Missouri, not as cold, 40. There's my 12 degrees. So I've got city A and city B. I found the difference, right? 40 minus 28 is 12. And then I have a measurement between them of 240 miles. I'm going to calculate my gradient. So the first step, I write the equation. Changing the value of a distance, I got that off page 1 of the reference table. Then I substitute. 12 degrees is my field value. So this number goes up top. 12 degrees. My distance always goes on the bottom. So if you sometimes, because I don't know what goes on the top, what goes on the bottom. Well, your distance is miles, right? You know that. That has to always go on the bottom. If it's in miles or kilometers, something like that. So 240 goes on the bottom. I plug that into a calculator. I got 12 divided by 240 equals, and I'm going to carry it out what I see, and it probably would tell you that on a regions. It would say carry it to the 100th place, because the first is tenths, 100th. I've got 0.05. I'm going to need my units. I got to put the degrees per mile. So not only the 0.05, but I have to have degrees per mile there. So that's my answer, 0.05 degrees per mile. Okay. On a test question, what I would do, and I'll probably give you a few of these to do on the next test in a few weeks, I would make this worth 4 points. 1 point for giving me the correct equation, and that's on the SRT. That's easy. I give you 1 point for what I call substitution, putting in the numbers, and I give you 1 point for the answer and 1 point for the units. So there's 1 point, 2 points, 3, 4. This is 2 points right here. Okay. Let's do another one here. This is a contour map, or again, a topographic map. Means the same thing. Using contour lines to show elevation. I've got X sitting up at this top of this hill at 3,500 feet. I've got Y sitting at 3,000 feet. and they're looking for the gradient between x and y. So how many feet per mile. All right, and it tells you the distance is measured in miles because they give you a little scale. Always look for the scale. They will give you one at the bottom of the map. So in this case, I know x is 3,500 and y is 3,000. That's easy. I'm going to subtract 3,500 minus 3,000. That's my change in field value. So that is 500. So I've got a difference in elevation of 500 feet. You might say, how did I know it was feet? Over here. They're telling you, and we haven't gotten into this, we will probably next week, what's called the contour interval. How much is each line counting by? So in this case, each line counts by 100 feet, right? If this is 3,000, this is 3,100, 3,200, 3,300, 3,400, 35, etc. So I know I'm using feet because they told me feet in this corner. So I've got x at 3,500, y at 3,000. That's 500 feet difference. I have to divide that by the distance. Now, when you do distance on a Regents, scrap paper, always use scrap paper. You're going to take a piece of scrap paper. You're going to line it up. I used a purple line here, but you're going to line it up between x and y. You're going to put a little mark for x, a little mark for y. You're then going to bring your scrap paper down to this scale. So what I did is I made a purple line here. Clear all this mess. There was my purple line, and then I just took that purple line and I dragged it down to the scale. I had to do a little rotate here. And so you can see the finished product is the same. So I could see what my distance is. Now in this case, you want to be very, very specific. They give you these little markings. These are 1/10 of a mile. So in this case, this is 0. I got 1 mile. And then I've got, this would be half, which is 0.5. I've got, what, 2 more markings there. That's 0.7, because you can see this is 0.8, 0.92. So I've got 1.7 miles. And yes, you have to be that accurate. You can't just, well, I think it's 1.5. Nope. You want to be very specific and very accurate when you measure distances. And that's why I tell kids scrap paper. You will have scrap paper on a test, or, use scrap paper, have some at home when you take these kind of questions. And you want to really make sure that you mark it off on scrap paper, the distance, and then bring that scrap paper down to the scale. Because in this case, it was very, very specific. So in that case, again, it was 3,500 minus 3,000, which was 500 feet. And then I'm going to divide that by the 1.7 miles. So I'll grab my calculator. 3,500. Oops, sorry. Whoa. 500. That's the difference. Divided by 1.7 gives me 294. Now, I don't know if it's didn't say in here. It probably would. It would say go to the nearest 10th. Most things in earth science, you go to the 10th place. So I've got 294.1. And again, units are going to be feet/mile. And you see they did write that. This was off of Regents. They put units must be included. So if a kid just wrote 294.1 and forgot to write the feet per mile, they lost a point. By the way, everything on a Regents is only worth 1 point. So in that case, yeah, the kid could have done the math the right way, but forgot the feet per mile, loses the whole point, which really stinks. So you want to make sure you put everything there accurately. So again, to do gradient, it was find the difference in elevation, which I took the 3,500 and the 3,000 and subtracted. That's where I got the 500. I used my little scrap paper, marked that off, brought it down to the scale. I got 1.7, and I divided that out. Change in elevation divided by distance. I got another one more here. So this time you're doing gradient, but you're not doing, this was an elevation gradient, feet per mile. Now you're doing an air pressure gradient, but you do it the same way, no matter what, whether it's temperature, this could say temperature, pressure, doesn't matter. Gradient is gradient. You use the same equation, change in a value over distance. So in this case, they wanted from A to B, and they're telling you your units, millibars per kilometer, which I wrote down here already for you. You just had to come up with the answer. So I look at A and B right up here. I can see A is at 1,020 millibars, B is at 1,016. So I subtract 1,020, right, minus 1,016 gives me 4 millibars. Again, I'm going to use scrap paper for distance. I would take my little paper, put it right on this line between, well, it wouldn't be a line there, but I would just line it up between A and B, my scrap paper, mark it off, bring it down to the scale down here. Always going to be a scale at the bottom of the map. So in that case, if I take that little purple line, I grabbed that with all that mess. That was pretty impressive, Mr. Rocco. And I'm going to rotate this guy, and I'm going to bring this guy up here. Oop, now I can't get it right. There we go. And you can see that's about 200 kilometers. So I had 4 millibars over divided by 200 kilometers. I grabbed my calculator. I plug that in. 4 divided by 200. I get 0.02. The 0 out front, kids will ask me, does it matter? Nah, this is insignificant. If you just put 0.02, that's fine. This 0 is significant, the one after the decimal. If you don't put this one, doesn't matter. But I got 0.02, and again, units, MB for millibar / kilometer. Be careful with units. If you don't know the universal symbol, like if you didn't know MB, then just actually write it out like that. Write millibars / kilometer if you're not sure of units. The one I know students will tend to mess up on is meters and miles. I've seen on Regents exams where students will, let's say it was feet per mile, a student will write feet, they know that one, and they'll put M for mile. That's not mile, that's meter, and I had to mark it wrong. So it's FT / MI. And I know I got students say, well, Mr. Rocco, how did I get that wrong? You didn't put MI. Oh. So always make sure, if you, when in doubt, I'd say write it out. So you could write out FEET / MILE if you're not sure. Write out the words just to be safe. And I think that's it. Yes. So I will post this video. Again, watch it, rewind, go back. If you're not sure how to do gradient or how to draw iso lines, the one assignment will have one. Again, if you have a printer, which I hope you do, if you don't, try to see if you can pick up a printer in the near future. It doesn't have to be an expensive one. Just get one that obviously prints. It can be just black and white if you want to get a cheap printer at Walmart or Amazon. Anyway, print out the assignment that has the iso lines where you have to draw them, and then what you can do is just use your phone or a scanner. If you have a printer scanner, that's another way to do it. Scan your homework in and it'll make it a PDF, and you can attach it to Canvas or take pics with your phone and then send those to me through Canvas. Okay, have a good week, and I will talk to you soon. Bye.